In this segment, we are going to start with a box, and we're just going to have a box that is flat on a flat surface like this. Let's make it a 10 kilogram box, and let's push on it with a force that we don't know yet. We're going to try to find out what force we need to push it on. So we have a 10 kilogram box that we're pushing to the right, but now we have friction between this box and this surface. And let us say we've picked some material so that the static coefficient of friction is 0.4 and the kinetic coefficient is 0.1. So like we've always said, the kinetic friction is smaller than the static friction because it's easier for when moving, for the box to slide along the top of all those little peaks and valleys. All right, so let's, in terms of the problem, let's start at rest. So the box is not moving right now. So since the box is not moving at rest, that means we are in the static realm. And the question is, what force is required in order to cause the box to start moving? So what force starts motion? All right, that's going to be our question. How do we figure out what that force is? Well, okay, so we have no idea really where to start, but we do have a process, and let's just start with our process and get as far as we can, and then we can think about what friction does for us. So first step of the process, start a coordinate system. Our coordinate system, since the box is moving flat, we will just have a normal x and y coordinate system where the box is moving in x and not much is going on in y. Second thing is our free body diagram. So let's take our 10 kilogram box over here and let's put a free body arrows on there. So we have mg pointing down, we have the normal force pointing up, we have this force that we are pushing that we don't know, pushing to the right, and we have friction, opposing motion. Force of friction is in the opposite direction. And that's it. So there's our four forces. Step 3, write down the equations of motion, some of the forces in the x direction and some of the forces in the y direction. So with some of the forces in the x direction, some of the forces in the y direction, what's going on in x? We have the force that we're pushing with, positive. We have the force of friction, that is negative, and that's it. So that equals mass times acceleration in the x direction. And in the y direction, we have the normal force that is positive, and we have the mg, which is negative, and that equals mass times acceleration in the y direction. Because nothing's going on in the y direction, we get to say that this is equal to 0, and immediately we can solve this and say F normal is equal to mg, and since this is a 10 kilogram box, it's 10 kilograms times 9.8 meters per second squared, which means that it is equal to 98 newtons. So I know my normal force is 98 newtons in this case. All right, and so far we haven't needed to use that, but we'll see in this case. What about in this x direction? How are we going to decide if the force, our original question, what force starts motion? So in this x equation, we can look at this x equation and ask that question. In this x equation, what force would start motion? We would start motion if we had an acceleration. So if the force that we are pushing with is bigger than friction, it will move. If we can't push as hard as friction, if friction wins, it will not move. So really the question we're asking, we're in the static case, we're saying, is force that we're pushing with bigger than or equal to the force of friction? And the bigger than or equal to, the equal to will be the limiting case, right? If it's exactly equal to, we're just on the border of moving. So that would be the minimum force required to start that moving, all right? So if the force is bigger than force of friction, if this is overall positive, it will start to accelerate. So this is the question we're asking. Is this true? Or what's the force required to make sure that it's true? Well, what's the force of friction? We have to go and use our basic understanding that force of friction is mu F normal. Well, that's easy, right? So we can say force of friction, the force that we're looking for, has to be greater than equal to mu F normal. And because we're in the static case, we're talking about mu static. Okay? But those are just known numbers now. We already calculated over here the F normal, so we're saying that the force has to be greater than or equal to mu static. Mu static is up here, 0.4. So 0.4. No units on mu static. Mu is just a coefficient, it's a number. And F normal, we already calculated, 98 newtons. So we're saying that the force that we're pushing with has to be greater than or equal to 0.4 times 98. And 0.4 times 98 is 39.2. So if the force that we're pushing with, this force over here, is greater than or equal to 39.2 newtons, then the box will start to move. So we have used the static friction case, and the static friction case, in conjunction with our understanding of the relationship between the friction force and the normal force, have found out that our minimum force to start the box moving is 39.2. If I push on this box over here with a 39.1 Newton force, it won't move. If I push with a 39.3 Newton force, it will move. And if I push at exactly 39.2, I will just overcome static friction and it'll start to move. Now the interesting thing is, once it starts to move, we move into the kinetic realm. So suddenly it becomes easier to start it, keep it moving. So a secondary question could be, if I push with this force, if I push this box with a 39.2 Newton force, what will the acceleration be? Acceleration will equal what? So now that we've decided that we can push our box 39.2 and it will overcome static friction, we can ask another question. Go ahead and push the box at 39.2 newtons. It overcomes static friction, and let's figure out the acceleration. So in some respects, we have to do this whole thing again, right? Although our coordinate system doesn't change, our forces don't change, and our Newton's laws don't change. The only thing that changes is that coefficient of friction. So I can copy down these Newton's laws. I know that from the sum of the forces in the x equation, the force minus the force of friction is still going to be mass times acceleration in the x direction. And I know that from the y direction, nothing changes. So in the y direction, I'm still going to have F normal equals 98 newtons. And now I can just plug in a bunch of numbers. I can say that force, 39.2, minus the force of friction, mu kinetic this time, times F normal, equals mass times acceleration in the x direction. But again, mass is a number, F normal is a number, mu k is a number, so 39.2 minus mu k is up here, 0.1. Force normal is still 98 newtons, equals mass, which my box is a 10 kilogram mass, times acceleration in the x direction. I mean, this is all just numbers, so I can solve this for acceleration in the x direction. 39.2 minus 9.8 equals 10ax. 39.2 minus 9.8 is 29.4 equals 10ax. So ax is equal to 2.94 meters per second squared. So now we have an acceleration for this box based on if there is friction, if it's kinetic friction. All right? So you can notice that if it's 39.1 static, nothing moves. 39.2, it moves, and immediately we dump to the kinetic case because it's moving, and we can find an acceleration. And if I wanted to find that acceleration and use that acceleration, like any other problem, I could say, how far does this go in 10 seconds, or how much time does it take to go 30 meters, or what's the velocity after 10 seconds. We can easily do that with this acceleration, but we had to first calculate the static case before we could calculate the kinetic case.